Alright, so let's take a look at Lee's lemma, which is needed to prove something called Lee's theorem, which is related to Engel's theorem, except rather than a statement about relating the concept of nilpotency to strictly upper triangular matrices, we relate solvability to upper triangular matrices. And so, in order to proceed with Lee's lemma, we actually have to introduce the notion of a weight space first. And so, the weight space is defined as following. Let L be a Lie algebra and V be a vector space over field F. Let pi be a representation of L in V. And let lambda be a linear functional in the dual space of L. Right, and so a linear functional is simply this linear map that takes vectors in the vector space, in this case L, and sends them to the field, the underlying field. And so the weight space V sub lambda of L is defined as following. V sub lambda L is equal to vectors in V such that pi of xv is equal to lambda of xv for all x in L. And so if you look closely, this resembles the eigenvector, eigenspace, eigenvalue stuff that you learned in linear algebra, except we're generalizing the notion. That is, rather than a fixed matrix acting on V, we have a whole bunch of matrices acting on V, and similarly, rather than a single eigenvalue, we have a whole bunch of scalars acting on V. But the idea is the same, is that you act on V with x, and then you get a scalar multiple of V that depends on x for all x in the Lie algebra. And so clearly 0 will always be an element of the weight space, regardless of what linear functional you choose. So we're only interested in the lambda for which we get more than just 0. So if V sub lambda of L is not equal to 0, we say lambda is a weight for the representation. And so we've actually seen an example of this in Engel's theorem where the weight was 0, and we'll see more. We'll continue to see more. One of the most important examples of weights are the roots, and that will be a tremendous part of this course, and so I don't want to spoil anything. I'll just kind of prime you with that. And so we can actually move on to Lee's lemma now. So let L be a Lie algebra over an algebraically closed field of characteristic 0, and we'll say F is the field. And we need this because, so far we haven't really been assuming many things, but if you want more results, you're probably going to have to get more structure. And so let I be a proper ideal of L. And lastly, let pi be a representation of L in some finite dimensional vector space V, and denote the restriction of this representation to I as pi sub I. And so this is kind of the assumptions. Then, for lambda in the linear functionals of I, in particular, as I said, we really only care about lambda, that's a weight, so maybe I'll say that here, lambda a weight. If V is an element of V sub lambda I, where V sub lambda I and not V sub lambda L is defined using the restricted representation here, this weight space, then if V is an element of this weight space, then for all x in L, pi of x acting on V is also an element of the weight space. So what we're saying is that you give me a weight with respect to the restriction of the representation, and then I get a weight space, and then if you give me any x in the Lie algebra and then it acts on the weight space, you stay in the weight space. Pretty cool result. And so the way we're going to prove this is actually not too bad. And we're going to start by actually kind of reframing what we want to show. So if we want to show this, right, we want to show if V is an element of V sub lambda I, then pi of xv is an element of V sub lambda I. And so the easiest way to do this is to reframe the problem in terms of an equation. And so this is an equivalent equation to show is that if V is an element of V sub lambda I, so I'll say want to show, if V is an element of V sub lambda I, then for all x in L, for all I in I, pi of I acting on pi of x V should equal lambda of I acting on pi of xv. And so this is just a fancy way of saying that pi of xv is an element of the weight space, right? It's identical, but now we have an equation to play with. And so the first step, it may not seem obvious how we're going to manipulate this. So the first step will be to kind of just use what we know. And we know that v is a weight vector. And so that means pi of I acting on v will give us lambda of I acting on v. The problem is we have this pesky pi of x in the middle. And so there's got to be a way to kind of reorient the order. And so we know that if you look closely, pi of I times pi of x is actually equal to pi of I bracket pi of x acting on v, plus pi of x times pi of I. All of that acting on v. So I'm just using the commutator relation. And so this thing here is equal to this stuff in the blue. And then because pi is a representation, this is pi of I bracket x plus pi of x, pi of I. And so rather than rewrite all this stuff, I just want to kind of illustrate the point that we're trying to show here. So let's get this color. So all of this stuff, right, if we call this is acting on v, right? So right here is acting on v. And so now we've moved I where we want it to be. So we know that this guy, pi of I acting on v, is lambda of iv. And similarly, because I is an ideal, this thing is an element of I, right? So we have pi of something in I acting on v. Well, because v is in the weight space, that should give you lambda of that something acting on v. And so what this thing simplifies to is lambda of that thing, which is I bracket x, plus pi of x, lambda of I, all acting on v. And that was just the left-hand side, and so we want to show this left-hand side is equal to our right-hand side, which is lambda of I, pi of x, v. But if you look closely, lambda of I is a scalar, and pi of x is a matrix, so they actually commute, and so we can cancel here, right? Lambda of I, pi of x, lambda I. And so we want to show, kind of, let's make sure we say centered, want to show for all x in L and for all I in our ideal, lambda of the commutator, two arbitrary elements, is equal to 0. So this is what we want to show. And so if we show this, that is equivalent to showing this condition in the blue here, and which is our theorem. And so the way we're going to do this is actually via construction. So we're going to construct a sequence of vector spaces. And so in order to do that, we're going to fix, let me find a good color first. Okay, yeah. Fix x element of L and choose non-zero v in our weight space, right? And so as I said, we're implicitly assuming that lambda is a weight, so that we can choose such a non-zero v. And so now that we've chosen this, we can define a sequence of subspaces as follows. We say for m that's a non-negative integer, we define w sub m, w sub n is equal to the span of the following vectors: v, pi of x acting on v, pi of x squared acting on v, and so on up to pi of x to the m acting on v. And then we define w sub -1 to be 0. And this will be because we will do some induction later on, and this will just make it nice to define it this way. And so the first thing we should notice is that these subspaces are contained in each other. So w sub -1 is contained in w sub 0, which is contained in w sub 1, and so on in w sub m. right? And so, and obviously because these guys are, it's just vectors in V, this has to be contained in V. So that tells us that at some point, right, because this guy has at most dim M. We see that at some point, there exists n such that Wn is equal to Wn plus 1 equals Wn plus 2 equals Wn plus 3, ... Right? Because otherwise V would, if that weren't the case, and somehow you're getting a new vector that's not in the span of the previous vectors each time, that would make V infinite dimensional, which is not what we said. We said V was finite dimensional. And so we know that there's some n such that Wn equals Wn plus 1, and so on. And so we're going to choose the smallest such n. So choose smallest such n, such n, meaning Wn minus 1 is not equal to Wn, but this, I don't want to write it again, is true. And so we won't need that n right now, but just keep it in mind, and maybe I'll come back up to it. And so clearly, pi of x acting on Wn is contained in Wn, right? Because of the way we've chosen n. And just to recap, I want you to look at this basis again, right? So that's why when you act on pi of x, it just bumps each one of these basis vectors up. And so with this in mind, we can show the following, right? So this is all of this. Just to recap where we are, we're introducing all of this structure in order to show this. We want to show this. And so we're getting there, and it may not seem obvious, but it will all come together momentarily. So let's switch colors. Let's go back to black. And so we can show for all m greater than or equal to 0, Wm is invariant under pi of I for all I in the ideal. And that pi of I, acting on one of the basis vectors, pi of x to the m, let's rewrite that, pi of x to the m times v minus lambda of I acting on pi of x to m v is an element of w sub m minus 1. So it'll be clear how all this comes together, but what I want you to see here is that what we're saying is that somehow pi of I acting on w x to m v, and then you subtract off lambda of I acting on the same thing. If you subtract that off, you send it from you send that vector, right? You send pi of x m v, which is an element of w sub m. You bump it down into w sub m minus 1. So we subtract off this bit, and we're going down into the lower subspace in the flag. And so this can be shown by induction. So can be shown by induction. And it's pretty straightforward, right? So when m equals 0, which is our base case, then it just becomes pi of I times pi of x to the m, which is pi of x to the 0's identity. So pi of I acting on v minus lambda of I acting on v should be an element of w sub minus 1. And so this guy should equal 0. But clearly it's equal to 0 because v is an element of v sub lambda I, right? That's how we chose v. So the statement is true when m equals 0, and now we want to show it in the general case. So assume this statement is true for m minus 1, right? I'm going to rearrange this statement, this part here, and try to use this fact that is true for m minus 1 to show this statement up here. So we have the quantity pi of I, pi of x to the m, v minus lambda of I, pi of x to the m, v. Okay, and we know this statement is true for m minus 1, so I'm going to actually do some trickery, and I'm going to add in 0 in a fancy way. So let's add, or let's subtract the quantity pi of x, pi of I times pi of x to the m minus 1 times v, and then let's add that pi of x, pi of I times pi of x to the m minus 1 v. Is that right? Yes, okay. So we're just adding 0 in a really fancy way. So now we're going to look at these two separate pieces. We're going to look at this piece, oops, and we'll call this piece 1, and then we'll look at this piece here, which we'll call piece 2. So piece 1 can be written as follows. It's pi of I, pi of x, times pi of x to the m minus 1 times v minus pi of x, pi of I, times pi of x to the m minus 1 v. Right? And so this is actually equal to pi of I bracket pi of x times pi of x to the m minus 1 v by just the commutator, and then this is equal to pi of I bracket x acting on pi of x to the m minus 1 v. And so clearly this guy here, right, is an element of w sub m minus 1, right? Yeah, so it is an element of w sub m minus 1, right, by the construction of w sub m minus 1. And then we have this thing here. This thing is an element of I, and we'll call it I prime. So we have this, is pi of I prime acting on pi of x to the m minus 1 v, right? And so we assumed all the way up here that Wm minus 1 is invariant under pi of I for all I and I. So directly by the inductive hypothesis, this thing, because this thing here is an element of w sub m minus 1, pi of I prime acting on something in w sub m minus 1 means that this quantity is an element of w sub m minus 1. Okay? So we see that this quantity here is an element of w sub m minus 1. Now we can move on to the second quantity. So the second quantity, let's change colors again, is the following. 2. We have, let me move over a little bit, pi of x, pi of I, pi of x to the m minus 1 v minus lambda of I, pi of x to the m v. And so this is actually equal to, let's see how we can rewrite this. So we can left factor pi of x, so it becomes pi of x times pi of x, oops, pi of I times pi of x to m minus 1 minus lambda of I. So actually, you know, I'll write it this way. Let's take a step back. It becomes pi of I minus lambda of I times pi of x to the m minus 1 b. Okay? And so what we notice right off the bat, this guy is an element of w sub m minus 1. And so by the inductive hypothesis, right, up here, all the way up here, right? If we plug in m minus 1 for m, we see that this quantity, so let's, oh, whoa, not sure what that is. Okay, so let's go back. Let's change colors. So this quantity now, by direct application of the inductive hypothesis, is an element of w sub m minus 2, right? And so what we have is, this is equal to pi of x acting on something in w sub m minus 2. So that means this entire quantity, entire thing, is an element of w sub m minus 1. So I hope that's clear. And so what we see, actually, is that this first piece is an element of wm minus 1, and the second piece is also wm minus 1. And so since wm minus 1 is a vector space, the entire piece is an element of wm minus 1. And so now we've proven this statement. We've shown that this is true. And so let me come all the way down and show where we are. Right? So just to reset, we want to show for all I and I, for all x and L, lambda of I bracket x is an element, or sorry, is equal to 0. And we know that for all I in I, for all x in L, pi of I acting on pi of x to the m minus, acting on v, minus lambda of I times pi of x to the m acting on v is an element of w sub m minus 1, which we said was equal to v, I'll say v element of v sub lambda I, v, so wait, let me take a step back, where w sub m minus 1 is equal to the span of v, pi of x, v, dot dot dot, up to pi of x to the m minus 1 v, where v is an element of the weight space. So this is what we know so far, okay? And so with this in mind, we can actually, I want to make an observation. We're saying that pi of I times pi of x to the mv minus lambda of I times pi of x to the mv is an element of w to the of w sub m minus 1. So that means, right, we can, with appropriate choice of scalars, we can say that pi of I acting on pi of x to the m v, like this, is equal to some linear combination of these guys, because it's an element of w sub m minus 1, plus this term here. So we have a naught v plus a1 pi of x v plus dot 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 a sub m minus 1 pi of x to the m minus 1 v plus lambda of I pi of x to the m v. Okay? So now consider the action of the pi i's. So consider the action of the pi sub I on w sub n, right, which we know is spanned by kind of here, except we just plug in n for n minus 1. And recall, n was all the way, this capital N, we define all the way back up here, right? So coming back all the way down, yeah, this is quite a long proof. And so if we consider the action of pi of I on Wn, right, if we look at the action on each of the basis vectors, the pi of x, the m, v, right, those are the basis vectors for w sub n, notice how what we end up seeing is that the matrix representation of pi of I with ordered basis as we've been saying, v pi of x v all the way up to pi of x to the n v is, as it looks like this: pi of I equals lambda of I whatever dot 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 whatever, and so it just has lambda of i's along the diagonal and has zeros below. So we see that this matrix is actually upper triangular, and so this is a square matrix. And so I just want to be extra clear how I'm getting this, right? I'm saying, right, so suppose this is the mth column here. This is the mth column, right? Pi of I acting on the mth column, which is our basis vector, pi of x to the m, of v, this is our basis vector, is going to give you a naught v plus a1 pi of x v, so on, so on. So these vertical guys are a naught, a1, am minus 1, and then finally in the mth spot, we're going to have lambda of I. And so that's where we're getting lambda of I along the diagonals by looking at this thing. And so we're almost done here. So we have pi of I is equal to this. This is the matrix representation. So now I want you to consider pi of I bracket x for arbitrary I and x. It should be the same thing, except with lambda of I bracket x. And so now I hope you see where we're going with this. Lambda of I bracket x along the diagonal. So 0 here, arbitrary here. And so because we have a lambda of I bracket x along the diagonal, if you take the trace of pi of I bracket x, right, this should equal n times lambda of I bracket x. Right, we're just adding up all the these guys along on the main diagonal, and so the trace of, there should be parentheses, of pi of I bracket x is equal to, so let me say it this way, trace of pi of I bracket x, right, is equal to trace of pi of I bracket with pi of x. And if you recall from earlier, the trace of a commutator is actually 0 because of the fact, because trace AB equals trace BA. And so this trace here is actually equal to 0. So we have this. 0 is equal to n times lambda of I bracket x. So because we assume that our field has characteristic 0, it's algebraically closed, this implies that lambda of I bracket x equals 0. And that is the conclusion of the proof. There's actually we don't actually have to assume that the field has characteristic 0. There's a slightly weaker condition, and I leave it to the viewer to determine what that condition is. But I just want to kind of outline the proof and what we did and restate the theorem. Okay, so let's go all the way back up here, right? We said that Lee's lemma is the following. Let L be a Lie algebra of an algebraically closed field of characteristic 0, and let I be a proper ideal, and pi some representation. Right? If we have a vector in the weight space for I, then the action of any vector in the Lie algebra on our weight space will stay in the weight space. And so we reformulated this as a new condition. So we started with that condition, and we want to say that that lambda of any commutator with something in the ideal and with something in the Lie algebra must give 0. That this commutator must map to 0. And so the way we did this was we constructed this weird set of upper triangular, this weird set of vector spaces, this flag, and then we did some algebra with the flag, and used like induction and and studied really the structure of this flag to realize that there's some nice upper triangularness going on here. And with that in mind, we using the fact that the trace of an upper triangle of a commutator has to be 0, and seeing that this lambda of I bracket x comes back into place, we were able to show our result. So that was kind of the botched summary of what we just did. But I hope it's clear. It's not at all like it's a simple proof, but it's not at all easy to write out. And I hope this explains the proof. This proof is, I've presented it as followed in some MIT lecture notes, which I'll attach. But really their proof is identical to Humphrey's proof, but his proof is just a little bit, I'd say, archaic maybe, like in the way it's presented. The notation is somewhat strange in the format. But other than that, they're pretty much the same. So that's Lee's lemma. We'll use this to prove Lee's theorem. And so that's it for this video. Thanks for watching.